Hi, welcome back. This is our third lab, so this is our week 2. I'm Abby.
I'm Brooklyn.
I'm McKenna.
And we're going to be working on clocks today.
So the first type of clock that we're going to be making is a sundial. This is a clock where we use the sun to gauge what time it may be. So at first we're going to mark the shadow that our toothpick is creating, and then we're going to wait for about 15 minutes and we'll check in.
Now we are going to look at something called a drip clock. So what McKenna's going to do is she's going to start the water and she's going to get it to go to just a drip. And then Brooklyn here is going to, every time it drips, hit lap. And as you can see, we're going to keep doing that, and then we're going to take the average of that to get the time of the drips. So here is our completed laps based by the drips.
So the next type of clock we're going to be making is a spring pendulum clock. So we're actually going to take 500 grams on the end of this spring, and then Abby is just going to start it oscillating. So she's going to gently pull it, and Brooklyn is timing and counting how many times the spring oscillates, and she recorded that by lapping them.
Okay, the next thing that we're doing is the swinging pendulum. So we added weights to the bottom of this, and we're measuring every time it crosses the center. So McKenna's gonna do the time, and Abby's gonna start at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, and here is all of our times that we got from lapping the swing pendulum.
So here is the data for each of the 3 clocks that we just tested. As you can see, the drip clock, we felt it was the easiest to construct and the easiest to time, but it had the most margin of error. As you can see, it deviates almost actually over a full second, while the spring pendulum was a lot more accurate, but also much faster. It was lapping every half second or so. So we felt like for the spring pendulum, if we wanted to do that with students, we would maybe use a looser spring because we wouldn't have to lap it quite as often and we could find a little more accuracy. The swing pendulum was our most accurate and pretty easy to construct and lap because you can see pretty clearly when it's crossing over the midline of the pendulum.
So after it's been about 15 minutes, you can see our original marking right here, and the sun has now moved as time has passed. So we can see in 15 minutes it moved this far. So then you can make another marking here and then wait another 15 minutes and see where it moves from there. So we wanted to see how long we could make the pendulum go. So we used the swing one. As you can see, it's been swinging for 1:25 and it is still going. So we dropped it from a shorter distance so that way the swing would be smaller. Whereas if we would have dropped it from up high, it would have continued to swing and it would probably have swung for a longer time. So as you can see, our pendulum is now done swinging. So that came out to be 4 minutes and 26 seconds. So now we're going to use this equation to figure out what the laps would be. This is what Brooklyn was doing on the phone earlier to figure these out. So now we're just going to throw it in here. So this number here comes from the length of our pendulum.
Okay, as you see, we were trying to solve for t. So we took the length over gravity of our pendulum and then over gravity, and we ended up finding 1.522 seconds when we used the square root.
Now we are going to make a histogram using our first swing pendulum that we did using the phone time. So here we've set it up so that our seconds, 0.72, increasing by 2, and then each of our laps, so we have a total of 10 laps. Here is our completed histogram. We did end up having to add some extras to get to our 10th time, which was 0.91. So now looking at it, we can see it that our average kind of falls at 0.79 in between these two, which we also found when we totaled up all of our laps and divided it by 10. But now you can see it mapped out through the histogram. So it has been another 15 minutes, and as you can see, our sundial did move from our last point, but the distance is different from what we can see. It would not be the most accurate, as a student could easily move it around and say this has been 15 minutes, but we know that it was here. So it's really kind of hard to tell if this would be the most accurate form of timing.
Okay, so we were deciding that the ease of construction It was a little bit harder for the pendulum ones because the sundial and the drip ones were super easy to set up, but we decided that they were not the most accurate rather than the other ones.
Yeah, and the resources that it takes to set up the drip one and the sundial are a lot more accessible for classroom teachers, where not everyone has access to springs and things to hold a pendulum.
Yeah, so that is it for today, and we will see you on Thursday.
We hope you feel better.
Welcome back. Today is Thursday, so day 2 of our lab. We're going to be looking at velocity and acceleration. Okay, so we're going to be looking at how fast we walk. So we're measuring the distance from the grass all the way down to the curb. So what Brooklyn and McKenna are doing here is they are moving it, and they're just continuing to measure until we've reached the end of the curb. Here's McKenna, and she is going to go ahead and walk. So hers came out to be 2.3 seconds for her to walk.
Okay, the way that we measure velocity is distance over time. So we put our distance, which was 144, over our time, which is 2.3 seconds, to get 62.6 inches per second.
So now we are going to be trying to measure the velocity of a ride. So we started by dropping a pin from Lago to Physics Hall, and we saw that it was 700 feet away from here at Physics Hall. So we set up a timer and we timed a ride right as it passed Lago until it got right here to Physics Hall.
So then we used the same distance over time to solve for the velocity of a car. So we saw that it was 700 feet, so we had to convert that to miles. So that came out to be 0.133 miles, and then it took it 22.7 seconds, so we had to convert that to hours, which is a really, really small number. So it was 0.00631 hours. So then we did our math. So we did that number divided by this number, and we got it was going at 21 miles per hour.
We are going to use 5 for our next thing, which is finding the acceleration that we have when we begin walking. We're using the absolute acceleration without g.
So McKenna's now gonna walk. So as you can see, she is accelerating forward as she continues walking. Now we can see her acceleration as she walked through the app. So her acceleration was 3.94 meters per second squared. Now Brooklyn is gonna do skipping, and we're gonna see how it's different. So now we're gonna see how her graph looks different. So here's Brooklyn's with skipping. So we see that her absolute was 7.04 meters per second squared.
Okay, so now Abby is going to try the same experiment but running. We can see Abby's acceleration in this graph, and her absolute acceleration was 1.76.
Okay, Abby's absolute acceleration was the lowest because she just started running really fast and then it like narrowed out at the end, or settled out at the end. And then the bobbing in our graph is from our phones going up and down like this. Okay, Abby has the blocks that she's going to hit together to make the sound, and she's going to all the way to that end of the hallway. And McKenna is going to all the way up to the other side of the hallway, and she's going to video Abby in slow motion, and then we're going to take the distance between them and over the time in the slow-mo video where it takes from when Abby can, like, you can visually see her hitting them together to when you can hear it in the video. Okay. Yep.
So now using the measuring app, I'm going to add a point, and I'm going to walk all the way to where McKenna was at the end of the hallway, and then it'll give me my total.
It was 60.28 meters.
So then we looked back at the slow-mo video that we took, and we cropped the video to right when Abby's hands come together, and then we find the time by listening for the sound. And we found that it was around 0.68 seconds when we saw the sound get made, and then we heard it at 0.84. So that means there was 0.16 seconds in between. We were about 60.28 meters apart after measuring, so we got that our speed of sound was 376.75 meters per second, which isn't too far off from the actual, which is around 343.
So today we worked on velocity, acceleration, and also finding the speed of sound, and that was it. So I'm Abby.
I'm Brooklyn.
I'm McKenna.
Have a great day.